So we've seen how to train a regression model to predict a numeric value. Now it's time to look at another kind of supervised learning, and that's classification. So Steve, what's that about?
Yes, classification is a technique we use to predict which class or category something belongs to. The simplest variant of this is binary classification, where we predict whether an entity belongs to one of two classes, often used to determine if something is true or false about the entity. For example, suppose we take a number of patients in our health clinic and we gather some personal details and run some tests, and we identify which patients are diabetic and which are not. We can then learn a function that can be applied to the patient's features and give a result of 1 for patients that are diabetic and 0 for patients that aren't. Or more generally, a binary classifier is a function that maps features x to produce a y value of 0 or 1. Now the function won't actually calculate an absolute value of 1 or 0. It will calculate a value somewhere between 0 and 1. And we'll use a threshold value to decide whether the results should be counted as a 1 or as a 0. When we use the model to predict values, the resulting value is classified as 1 or 0 depending on which side of the threshold line it falls. Because classification is a supervised learning technique, we withhold some test data to validate the model using the known labels. Classes where the model predicts a 1 for the test observation that actually has a label of 1 are considered true positives. Similarly, cases where the model predicts 0 and the actual label is 0 are true negatives. If the model predicts 1, but the actual label is 0, that's a false positive. And if the model predicts 0, but the actual value is 1, that's a false negative. The choice of threshold determines how predictions are assigned to these classes. In some cases, a predicted value may be very close to the threshold, but may still be misclassified. You can move the threshold to control how the predicted cases are classified. In the case of the diabetes model, for example, it may be better to have more false positives, but reduce the number of false negatives so that more people who actually have diabetes are correctly identified. The number of true positives, true negatives, and false negatives produced by your model is critical in evaluating its effectiveness. The counts of these are often shown as what we call a confusion matrix, and this provides a basis for calculating performance metrics for the classifier. The simplest metric is accuracy, which is just the number of correctly classified cases divided by the total number of cases. In this case, there are 5 true positives and 4 true negatives, and there are also 2 false positives and no false negatives. That gives us 9 correct predictions out of a total of 11, which is an accuracy of 82%. Now that might seem like a really good result, but perhaps surprisingly, accuracy isn't actually all that useful to measure a model's performance. Suppose, for example, only 3% of the population is diabetic. I could create a model that simply always predicts 0, and it would be 97% accurate. But this model is completely useless for identifying potential diabetics. A more useful metric might be the fraction of the cases classified as positive that actually are positive. This metric is known as precision. In other words, out of all the cases classified as positives, which ones are true and are not what we call false alarms? In this case, there are 5 true positives and 2 false positives. So our precision is 5 of 7. which is 71% of the cases identified as positive, really are diabetic, but 29% are false alarms. In some situations, we might want a metric which is sensitive to the fraction of positive cases we correctly identify. We call this recall, and it's calculated as the number of true positive divided by the combined true positives and false negatives. In other words, what fraction of positive cases are correctly identified? In this case, there are 5 true positives and no false negatives. So our recall is 5 out of 5, which is 100%. So in this case, we are correctly identifying all patients with diabetes. Recall actually has another name. Sometimes it's known as the true positive rate. And there's an equivalent rate for false positives compared to the actual number of negatives. In this case, we have 2 false positives and 4 true negatives. Our false positive rate is 2 out of 6, which is 0.33. Now you may remember that the metric we got were based on a threshold of 0.3, and we can plot the true positive rate against the false positive rate for that threshold like this. If we move the threshold back to 0.5, our true positive rate becomes 4 out of 5, or 0.8, and the false positive rate is now 1 out of 6, or 0.16, which we can plot here. Moving the threshold further to, say, 0.7 gives us a true positive rate of 2 out of 5, or 0.4, and a false positive rate of 0 out of 6, or 0. If we plot this for every possible threshold, we end up with a curve line like this. This is known as the receiver operating characteristic, or ROC curve. And the area under this curve is known as the AUC, which stands for area under the curve. It's an indication of how well the model predicts. Generally, you want to see a large AUC with the curve staying as close as possible to the top left corner of the chart. A perfect classifier would go straight up the left of the chart and then along the top, giving an AUC of 1. You can compare the curve with a diagonal line, which represents how well the model would perform if you simply made 50-50 guesses, which has an AUC of 0.5. But in this case, our model has an AUC of around 0.9, so it definitely outperforms guessing.